Thank you, Romain. So, good morning, everyone. So first, I need to apologize because you obviously came to listen to Valentina, and now you see me. So I will be giving a kind of appetizer, but the main course will be given by Valentina. And so as Romain said, we will talk about light matter interaction, so it's a very general title, but the central concept that Valentina will use is this local density of states. So we already heard about local density of states on Monday with Paloma. So I will go a bit deeper into the introduction of the concept, because this is what Valentina asked me, and then she will go on with the way you can measure that in real systems. Okay, so I will basically be answering two questions. So as we saw on Monday, you can connect this local density of states to Green's function. So I'll give you three perspectives on what this connection, how you can, let's say, derive this connection. But essentially, that will give a meaning to this quantity, I guess, I hope. And then I will answer, the basic question is, why do we call this a local density of state? Okay. All right, so the first perspective to introduce the concept is to start with equilibrium fluctuation. So I will be talking about optics, so electromagnetic fields. So a first approach could be to say, okay, you have a system, it can be a structured system. Now assume you put it in a cavity at thermal equilibrium. So as you know from statistical physics, then you have a fluctuating field inside, okay, an electromagnetic field that is at equilibrium with the material degrees of freedom. And from linear response theory, you can show that if you are interested in the correlation function, so at a given frequency, you look at the correlation function between the field fluctuations at two different points. It's a vector field, so you even look at vector components. Okay, Ij means the vector component of the electric field. Then you have this fluctuation distribution theorem that tells you that it's given by this Bose-Einstein factor. This is equilibrium fluctuations. But you have a prefactor, and this prefactor is the imaginary part of the susceptibility of this observable. So it's the response function. And for the electromagnetic field, the response function is this Green function. So the Green function is a classical concept. It's really the connection. It's an antenna theory concept. You put a dipole here. You want to know the electric field here. And that's just the linear response. Okay? So if you take the imaginary part of this function, that gives you this correlation function of the electric field. From that, you can do a lot of things. You can study the spatial coherence of the thermal fluctuation and so on. This is not the purpose today, but now if you make R and R prime coincide and you sum over all components, then what you can compute is this energy density. So U of R here is the equilibrium energy density associated to the electric field. Okay? But on the other end, you probably also know or remember from statistical physics that you can compute that from a different approach. You can say, okay, I want an energy density, so energy per unit volume. So you have to take the product of three terms. So first, I take the number of electromagnetic modes at a given point, which is the density of state. But here it's a local density of state, the contribution of modes at a given point. You multiply by the average number of photons per mode, which is this Bose-Einstein factor, and by the energy of one quantum, and then you get the energy density. So now if you take this to compute this, you identify and you get this expression of the local density of state. So that's the first way to understand it. You have a prefactor, okay, here I just forgot prefactors, but if you do the prefactors correctly, you find that trace here means that you sum up over the trace of this tensor, okay, so it's a trace over the polarization degrees of freedom. Okay, so that's one way to understand how this thing, which is an antenna quantity, gives you a local density of state. By the way, you can do one step more, because if you think about electromagnetic field, you also have a magnetic field, okay? So if you compute the full electromagnetic energy density, you play the same trick, and then you can even define an electric contribution and a magnetic contribution to the local density of states. Today, Valentina will talk about electric local density of states. Okay? Electric dipole transition and so on are much stronger in usual systems than magnetic transition. So we will focus on electric part, but I just wanted to mention that you can use this perspective to define also the magnetic contribution. Second point of view. And Paloma talked about that on Monday. Another point of view, say now let's assume you have a system, a structured system, okay, and you put an emitter. So at this stage, it's just a classical emitter. So you have a dipole, electric dipole, that you drive. Okay? You have an external operator that drives the amplitude of a dipole oscillating at omega. And you look at the time average emitted power. So as you know, you can compute it this way. Okay? P is just the dipole moment. The star is the complex conjugate. And E is the electric field that the dipole feels at its location. So now use the Green function. So it's just the linear response, okay, that connects. Sorry, I'm mixed up with this. That connects the electric field at one point to the source at another point. So if you plug this into this, then you get this expression. So you see again this imaginary part of the Green function at coinciding points that appears. So U here is just a unit vector that defines the direction of the dipole. Okay? So if you would sum up over all possible direction of U, then you would find here the trace of this tensor again. Okay? But since the dipole has a given orientation, this is what you get from the calculation. So by the way, this is something you can also connect to antenna theory, because people that work with antennas, so you know that if you load an antenna with a current, so assume you have a small antenna, like a dipole antenna, so the size D is much smaller than the wavelength here, it's an electric dipole antenna. You know that the power that is emitted, you can compute it from an impedance. Now we can consider this antenna as an electrical circuit. And the power that is a loss for the antenna is connected to the real part of the impedance. You can also show that the real part of the impedance takes a similar form. So there is a connection between local density of state and impedance. Okay, I just wanted to mention it. Although maybe we're not going to use it too much today. So now what happens if you have not a classical electric dipole, but you have a two-level emitter, or let's say a quantum emitter? So now at the location of this classical source, I assume you have a two-level system. So I can define for the system a transition dipole, and I have the Bohr frequency, okay, that is connected to the difference in energy between the excited and ground states. So you can move to the quantum expression of a spontaneous decay rate. Now, one observable could be at t equals 0, this emitter is in the excited state. And then after some time, you detect a photon. Okay? And from that, you can define a spontaneous decay rate. Valentina will come back to this. So the question is, how can you compute the spontaneous decay rate? So you can use linear response theory and perturbation theory in quantum mechanics. But you can also move from classical to quantum just by using a correspondence principle. So you say, okay, I can start from the classical power that is emitted, so the previous expression in the previous slide. So you change the frequency of the classical emitter by the Bohr frequency. Here you have a power, so you divide by the energy of each emitted quantum, and then you get a decay rate. And you replace the dipole moment of the classical antenna by transition dipole. You have a factor of 2. So you know, very often when you do a theory, you fight with a factor of 2 somewhere. But this factor of 2 is, it's an important factor of 2 because at the end it's a factor of 4. But you know, it's because when you define P at a given frequency in classical physics, you use a Fourier transform, so you have positive and negative frequencies. In quantum mechanics, when you define, for example, a transition dipole, depending on whether you are interested in absorption processes or emission processes, you give a clear meaning to positive and negative frequencies, so you have to be a bit careful. So this factor of 2 has to do with the fact that this guy, you define it only with positive frequency. Okay? So it's not a factor of 2 that we add by hand to say, okay, just to get the correct prefactor, I have to put a factor of 2. I mean, it has a clear meaning. And then you get this expression. So now it's the spontaneous decay rate. Valentina will show you how in practice you can measure that. You can even image that in complex systems. And again, you see this magical imaginary part of Green function that appears with U, again here, the direction of this transition dipole. Okay? So that's a nice way to move from classical to quantum. If you're interested in those kind of reasoning, I really recommend this book. It's an amazing book. It's also good to meet, say, Max Born did that before I show you, because then you believe me. Okay, okay, so now why do we call that the density of state? So because very often when we compute transition in quantum mechanics, we like to write that in the form of a Fermi-Golden rule. Okay, so you have here the transition, let's say the matrix coefficient for the transition, And you have here the density of states for the final states, so that are the states that are ready to accept the emitted photons. And again, that defines the local density of states. So if you identify, then you'll find again this expression. So you can, so that's the second point of view. You can keep in mind that if you have an oriented dipole, okay, then you need to get, okay, this is a second rank tensor, so you need to project this tensor over the direction of the dipole. If you want the full density of state, then you have to sum up over ux, uy, uz, and then you get the choice. Okay, just that can give you a factor of 3. Okay. The connection between the spontaneous decay rate of a quantum emitter and the power emitted by an antenna also allows one to get this splitting between processes that give rise to photon emission. For an antenna, that would be far-field radiation, and absorption, because if you put the emitter or the classical antenna in an environment, then part of the excitation can go to internal degrees of freedom, and at the end you will heat up, let's say, the environment. Okay? So this is a splitting that is natural for the power emitted by a classical antenna. You can directly translate it into the density of states. So you can define this way a radiative and non-radiative contribution. And I think that Valentina will speak about that. And that's a very simple example that we computed a long time ago when you have a two-level system interacting with a small particle that is itself treated in the electric dipole approximation. So it's dipole-dipole interaction. And when you move this emitter closer to the particle, then you see how the full density of states evolves with distance. And this is the non-radiative and radiative contribution. You see that at short distance, in that case, it's an absorbing particle. Then when you go very close to the particle, then non-radiative processes win. And that's also something that Paloma discussed on Monday. Now there is a third way to understand how the local density of state enters light-matter interaction. So the third way is we to take a scattering point of view, which is very familiar to this community. So assume now you have a small particle, or it can even be a two-level system. The only assumption here is that it's small enough so then you can describe it in the electric dipole approximation. So it's described by a polarizability alpha that is frequency dependent. And it's in an environment, you shine light on it, and this guy interacts with the environment, and the question is, what is the effective polarizability given the environment? So to answer that question, you can think about the process this way. So the particle is excited, so alpha 0 is the bare polarizability, the polarizability that you would get in free space. Okay, so given the environment, the particle does not feel the incident field, but the excited field. So the field you get in the environment without the particle. So that gives you the first term. But the second term comes from the fact that now you have an induced dipole, but it radiates, and you have back reflection. So you have interaction up to infinite order. Okay, could be multiple scattering if you want, to use the vocabulary that we like in this community. And then you can describe it again with a Green function, okay? Because this is an electric dipole. So it radiates with a Green function, and you have radiation back to it. Okay, so this is the part of the Green function that accounts for the environment. So it's the full Green function minus the vacuum Green function. Okay, the interaction of the particle or the two-level system with itself through vacuum is already included in this guy. Okay, so you only need to take the part that is the additional contribution to the Green function to the environment. So this is this S operator here. Okay. So that's the way you can write the induced dipole. And then you can define an effective or a dressed polarizability by saying that you also want to write P in the form of an alpha to be determined, excited by this external field. Okay? So this has to include all those processes. Okay? So it's easy work to show that from this to this, you get this equation that defines the dressed polarizability in terms of the bare polarizability, the vacuum polarizability, and the interaction with the environment. Now, if you want to get the eigenmode, or at least the eigenfrequencies, then you need to define the poles of this guy, or the zeros, or 1 over alpha, and you get this equation. So this is the Green function of the environment, and this is the polarizability of the emitter alone in free space. Okay? Two known quantities. Now, if you solve that for omega, you get the eigenfrequencies. Okay? This is very known stuff, okay? But it's just coupled oscillators, if you want, okay? One oscillator is this guy, and the other one is this guy. So you can do that. You can do a lot of interesting things with this. But I just want to mention that in the so-called weak coupling regime, you'll find again the expression of gamma in terms of the LDOS. Weak coupling means that assume this guy has a resonance with a width, a line width that is gamma 0. So it can be a resonant particle. It can also be a two-level system. Okay, you have a probability for this two-level system. So in that case, gamma 0 would be the spontaneous decay rate in vacuum of this two-level system. And now you assume that the environment is weakly frequency dependent. So it's not a resonant cavity, but it has a smooth response. So in that case, when you solve for this, you can use first order perturbation. And what you find is something that you know, is that in this weak coupling regime, now the oscillator, the two-level system, or the particle in the presence of the element has a resonance frequency that is shifted and a line width that is broadened, okay? And by computing the eigenfrequencies from the previous equation, you directly find that the broadening, which is the change in the local density of state, is again given by an expression like this. Okay, so that's another way to derive the relation between gamma and the local density of states. That's the first perspective, the third perspective. I'm not using strong coupling, but this approach also includes strong coupling. Okay? Now, if you assume that the environment is resonant, then you find that you get a splitting, you get the RB frequency, and so on. So this is not weak coupling. You have additional parameters that enter this story than the local density of state, but just to mention that the same formalism can be used for both. So I'm almost done, but I have to finish up with something. Why do we call that a local density of states? Because I told you it's the imaginary part of the Green function. It enters the expression of different observables, and you'll see how we measure that. But why do we call it an LDOS? Okay, so probably the best way to understand that is to take an example where you can explicitly write an eigenmode basis for the electric field. So assume that your system is lossless and it's in a cavity. So you have neither absorption losses nor radiation losses. Okay? So in that case, you can precisely define eigenmodes with eigenfrequencies and eigenvectors for the electric fields. And then you can define the density of states. So you know that the global density of states per unit volume is given by an expression like this. Okay? Every time the frequency coincides with the mode, you get a delta function. It's a spectral density. So if you integrate this over frequencies, then you get the number of modes per unit volume. Local density of state is you put some additional information. You want, at a given point, to weight the summation by the intensity of the eigenvector. Okay? So how you have many modes, and at a given point, you want to see how many cross and what are their strengths. Okay? So you add some information. So that's the definition of the local density of states. And now, okay, you have to believe me that you can get an expression like that, but if you are able to write eigenmodes, then the Green function, you can get an expression. It's not so complicated. Huh? But this expression, you see that you have the eigenfrequencies and the eigenvectors here. So since you are able to write this explicitly, it's very easy to show that if you take the imaginary part, you see this term starts to look like this. You take the imaginary part, and this becomes this, and you find again the expression. So if you do reverse engineering, you start from that. In that particular case, actually, this is this. Okay, so you can get this picture saying that now, if you're not in a lossless cavity, this is a generalized local density of states. Okay, by the way, if you have weak losses, you can show that the expression becomes something like that. Okay, now the delta function becomes a bit broad, and you get a sum of Laurentian, and still you can get something like that. You can use quasi-normal modes if you want to give a meaning of an expansion like that, even when you're beyond the weak losses regime. And my last word will be about Purcell factor, because that's also a keyword that you sometimes have in those light matter interaction talks. So Purcell wrote this paper. So that's the full paper. Huh? He never wrote any paper about Purcell effect, but he wrote an abstract for an APS conference. So that's the full abstract, where he says that if you put an emitter in a cavity, then you have this factor that speeds up the spontaneous emission process. Okay? So if you want numbers, so it's a good matrix, right? The number of citations per line. Now, you try to beat it with your papers. Okay. So just keep in mind that this expression of the local density of states I've been showing, in the particular case of that paper, which is a single mode cavity, gives you exactly the expression of Purcell. By the way, nobody really knows how he got this calculation. It's not only a guess, because you have the 3/4 pi squared prefactor, which is right, so it's probably a calculation. But if you do the calculation from the imaginary part of the Green function for a single mode, then you get exactly this. And you get, this idea that the factor that speeds up or that enhances the spontaneous decay rate is the Q factor of the cavity divided by the volume. So this gamma over gamma 0 is imaginary part of G. You can consider it as a generalized Purcell factor for a case that is more complex than a single mode cavity. So that's the summary. Before I give the floor to Valentina. So you can write the density of state in terms of an antenna theory concept that is the Green function. It can be measured from the spontaneous decay rate because gamma is directly proportional to this. It generalizes the Purcell factor. You have relative and relative contribution. You also have a magnetic part, but not be discussed today. And I think it's a good time to transit to the main course. Thank you for your attention.
Right. Can you hear me fine? Yes. Okay, so, well, first of all, I want to thank the organizers for this invitation. I'm very happy to be here. And I must say that, well, I was supposed to take all, to give all the course, but when I knew that Remi was in the room, for me it was just natural to ask him to do this first part because I must say that it is like 16 years that we talk about local density of states. So for me it was like normal to ask him to do the theoretical part. Now we move to experiments, we move to measurable quantities. And okay, the first thing that I would like to tell you is that, so what Remi showed is that there is a relation between the decay rate of an emitter in an environment and the Green function that describes the environment. But in practice, how do we measure that? So measuring the decay rate of an emitter, gamma, the decay rate is contained in this expression, which is the decay probability of the emitter in a given environment. So it means that if you take a two-level emitter and you put it in the excited state, and then you ask yourself, what is the probability that this emitter spontaneously decay between the time t and the time t plus delta t, you find in a very simple way, it just follows Poisson's distribution, that it is an exponential decay and with a characteristic time constant, which is 1 over gamma, the lifetime of the excited state, and therefore gamma is the decay rate. And therefore, in practice, how do we measure that? We use a pulsed laser. Here you have the excitation pulses. And we measure after each excitation pulse what is the delay between the excitation and the emission of a fluorescent photon. We repeat this experiment like 1,000,000 of times. We put all the delays that we measure in a histogram that you see here, and we recover exactly the probability, the decay probability between the time t and the time t plus delta t. And experimentally, this is what we find. So this is a log scale. This is the delta t, okay, the histogram of the occurrences of the delta t, this delay. And this is what you find. It's an exponential decay, a very clean exponential decay. This is what you find for a fluorescent bead, which is doped with dye molecules. So as you can see, the lifetime for this kind of fluorescent molecules is about 5 to 10 nanoseconds. You can also have other fluorescent emitters like quantum dots. For this kind of emitters, the lifetime will be more of the order of 20 nanoseconds, or NV centers in diamond, for which the lifetime is even longer. So this is one of the measurable quantities. But if now you just excite the emitter and you just look, you count the number of photons without paying attention to the time between the excitation pulse and the emission of the photon, you just count continuously the number of photons emitted, then you can measure the intensity of the fluorescence emission. And here you see for a fluorescent bead, a very long-lasting and stable fluorescence. And I would like to keep your attention on the different time scales that you have here. These are nanoseconds and these are seconds. Okay, so far so good. So this lays the basis for the study of light-matter interaction between, by using emitters to probe the environment. Now, in this framework gave really a push for the development of nanophotonics in the last 30, maybe 40 years. And with a lot of big challenges that are still there. For example, so if you want to sculpt light at the single photon level through its interaction with the environment, you have to know how to fabricate a specific environment in which the local density of states is exactly as you want. So as Remi told you, gamma over gamma 0, which is equal to the variation of the local density of states, depends on the green function of the environment. So one of the questions is, how do I shape the environment in order to have a very high Purcell rate, a very high gamma over gamma 0? The second question is, well, okay, now I fabricate the environment. How do I do to put the fluorescent emitter in this specific position of the environment? And so one of the challenges is to control the position of the emitter, to control it at the single emitter level, to image at the single emitter level this interaction with the environment. And of course, another challenge is to model the interaction with the environment. So research has been pushed in order to try to solve these challenges in different directions. And here I just summarize some of those, but well, it's just to give a very quick overview. So we had the great development of integrated quantum optical nanocircuits, lasers on chip, circuits on chip, the development of very precisely fabricated environment like nanoantennas. If you want if you are able to increase the emission, the photon emission by the emitter, you can go to very bright single photon sources. And also, of course, as I was telling you, if you want to increase in a very controlled way the interaction between the emitter and the environment, you want to develop super resolved, you want to develop ways to put the emitter in the environment, and also a way to image this interaction in a super resolved way at the nanometer scale. So in my group, we worked on different topics arranged in 2 different axes. But today I will only talk about this first part. So the first axis is the measurement of the local density of states in nanostructure media. And the second one is the energy transfer between fluorescent emitters in weak and strong coupling regime. Because yes, it is true that if you are able to shape the environment in order to increase the coupling of the emitter with the environment, then you can also increase the coupling between 2 emitters through the environments and see quite interesting things. But I'm not going to talk about this topic today. Okay, so what do we need if we want to image the local density states at the nanoscale? We need mainly 3 ingredients. We need to be able to position the single emitter with nanometric precision in the environment. We have to be able to address it, and we have to be able to detect its fluorescence intensity and lifetime. The very first way to do it, the very easiest, I would say, way to do it, is to perform statistical measurements. What does it mean? It means that here you have your nanostructure sample. Okay, here this is a glass cover slip on which you have whatever nanophotonic sample, and then you randomly spread single emitters on the top of the sample, and then you couple that with an optical microscope, and you shape the optical system in order to be able to address a single emitter and to detect its fluorescence. So I have to say that when you do this kind of measurements, you are able to address the emitter, you are able to detect the fluorescence intensity and lifetime, but you are not able to position it in a well-precise way. I mean, you're just randomly spreading emitters on the top of the sample. And so a question which is, I think, quite straightforward to ask is, can we really extract interesting physics from this kind of measurements? And I will show you that the answer is yes. And the example that I take is actually the first paper that we published together with Remi. It's about random gold films. So what are random gold films? If you take a glass cover slip and you evaporate gold on the cover slip, and you increase little by little the effective thickness of the gold layer, you come from, I don't know if you can see it, but here there is a first sample. So these are different cover slips on which we evaporate different thicknesses of gold. So here, in the very first sample, you have a very little quantity of gold, and gold clusters are arranged in spherical, very small particles. Spherical, I mean rounded shape, very small particles, which give this pink color to the sample. If you go on the other side, when the film is almost continuous, you have a color which is green in transmission, but it's already goldish in reflection. And in this intermediate regime, you have a very nice blue color. This regime is the very interesting one. And in this regime, gold clusters are arranged and form worms, like here, that connect to different sides of the sample. In this regime, you have, if you measure the spectra, you have the appearance of a very broad absorption plateau that covers from 700, 600 nanometers to all the infrared range. And this is responsible to the blue color that you find here. And it is known that these, on on these kind of samples, you have very bright and very localized hotspots in the intensity. And so, what happens when we measure the local density of states? What happens when we spread emitters on the top of the sample and we measure the decay rate of each one of those? So here I report the histogram of the decay rate for the two different samples. Here is the one, the pink one, the one with small, very small particles, and here is the blue one, the one with long worms. So what you see is that already it's the proof of something that Remi already said, that the decay rate depends on the environment. So you have a shift in the decay rate distribution towards larger decay rates when you go from this sample to this other one. But more interestingly, what happens is that you have a broadening of this distribution, and you have some points here which show quite large gammas, which are not present here. I must say that when we saw this histogram the first time, we were discarding this data because we thought there were just error in the experiment. And at the end, we discovered that the physics was in this very low probability, these data that occur with a very low probability. And what we could show was that exactly, the presence of this point here showed that you have large LDOS fluctuation on this kind of films, which, by the way, are fractals. So the arrangement of the clusters here is fractal. And these large fluctuation of the local density of states here was the signature of the presence of localized modes on the sample. There is a very simple way to understand it. If you imagine that you measure the local density of states on all the sample, you can imagine that you have like a mean value, let's say, here. Okay, but time by time, you have a very localized, a region in which the local density of states is very localized and very high, which corresponds to that. And so you have like a flat behavior, a peak, and then flat. And then this shows that the local, this shows very well why the fluctuation of the local density of states is related to the presence of localized modes. I don't.
And maybe it's obvious, but why does it range in such different behaviors for the different effective thicknesses? And is effective thickness the same as filling factor on this x-axis?
Yeah, it's related to that. Actually, the filling factor is the part of gold with respect to the part of glass. But sorry, I didn't get the question.
Why does the gold range so differently for the different effective thicknesses?
Why? This is a very good question. It's due to how the different grains of gold interact during the deposition process. It depends on the temperature of the substrate. It depends on the speed of the deposition process. It depends on a lot of things.
Okay, so this you can also control and have a difference.
Yeah.
You have a percolation threshold. At some point, you have percolation cluster, those worms, and then at this percolation threshold, you start to get this fractal behavior. Okay, so it's a known percolation process in 2D.
Sorry, there was another question.
Why do you orient the glass slide like that? Why not flip it, or why not have the emitters on gold directly? I have no clue.
Why we don't flip it?
Why illuminate it from this side, or why not have the emitters on gold side? Why this particular geometry?
This is just because, well, it's easier because the emitters were just spread on the sample, and then if you flip it, you have to put another cover slip to protect the sample. Well, it's just for practical reasons.
So this would be possible if you can put them, for example, directly on gold.
This is the question. Okay, yeah. No, yeah, of course, yeah. I didn't get to the all the details because it was too long, but yeah, okay. So you can also decrease the thickness of the spacer, okay, and put the emitters directly on the sample. That's true. This will shift all the distribution of gamma towards larger values of gamma. So I must say that now I don't have the numbers in mind because it's quite a long time ago, but this was one of the very first experiments in which we were measuring the lifetime, and we didn't, I mean, the time resolution that you need to measure these kind of events is already quite large, okay? Or small, I mean, a very good resolution, time resolution. So we didn't want to be too much close to the...
That's why the spacer.
Yeah, that's why the spacer, yeah. And by the way, we have another paper in which we show that by changing the thickness of the spacer, you have a change in the mean value of this distribution.
Is the spacer also like manufactured by
Yes.
yourself? Because it's only 40 nanometer.
Yeah,
And
we
can
were.
you imagine like physically how how it's definitely very fragile, I think.
Yeah, it's true. Well, now, you know, nowadays it is also possible to do very, very thin spacers, like 5 nanometers or 10, or yeah. In this case, we were just depositing silica on top of the gold film. But you can use polymers, you can use other materials, and have a very nice and controlled spacer with a very small thickness. And there was another question.
So did you find out where spatially these localized modes are, or can you not distinguish that?
No, in this experiment we couldn't, because we were spreading the emitters everywhere in a random way. Then, yeah, it's true that if you pick one of the emitters and you move it in a very controlled way on the sample, you can really make an image of the local tensor states.
So are they like at the worms, or don't you know?
I don't know. But it's a good question. But it's, well, a question which is a bit hard to answer, because you see the worms are quite small. Huh? This is 50 nanometers. The glass inclusions are very, very small. So you need a very high resolution in order to do an experiment, as you said. And you have to combine different kinds of images, as TEM images, for example, and optical images, and to recombine the two experiments in order to know where these emission take place. Okay? Okay, so this was about statistical measurements. But as I said, and that was a very good transition, actually, this question, the first point was, the first ingredient, I mean, was to be able to position the emitter in a very specific location in the environment. And that's why a lot of people, and also our group in Institut Langevin, decided to use near-field scanning probes. What is a near-field scanning probe? It's the tip that you see here. Okay, you can use it in different ways, but today I'm going to focus on only one. So this tip is a very tiny, elongated tip with a tip apex of the order of a few tens to 100 nanometers. And thanks to an electronic feedback, you are able to put the tip really close to the sample, like either in contact with the sample or at very like 10 nanometers from the sample. And thanks to that, it is possible to do several things. So if you look at the literature, you find mainly 3 blocks of experimental, let's say, approaches that people take. So you can either put the nanostructure on the tip, so you shape the tip, the environment is on the tip, and you have the fluorophores on the sample. Here I just put two examples. Here it's about bow tie antenna on the extremity, on the apex of the tip. Here is another realization. You can put the fluorophore on the tip and then scan it on the top of the nanostructure environment. So here it was a quantum dot. And here, this is something that I really like. It's quite impressive. The tip and the cantilever is made of diamond. This very small thing is the real tip. It's made of diamond. And they were able to put a single NV center at the very extremity here of the tip. And then the third possible approach is like a pick and place approach. So here you see this is the tip. You have nanocrystals on the sample, and then you push the nanocrystals in the position that you want. These are the emitters. Or the other way around, you have the emitter which is somewhere on the cover slip, and you can push with a tip the structure. So here, gold nanoparticles around the nanocrystal, and monitor how the local density of states is changed. So at Institut Langevin, we decided to develop a near-field fluorescent probe. So here you have the tip. It's a silica tip, which is made by an optical fiber, a tapered optical fiber, on the extremity of which we were able to graft a fluorescent emitter. Here, 100 nanometer large polystyrene bead doped with fluorescent emitters. And then we were able to keep it at a constant distance of 15 nanometers from the sample, and then to scan it on the top of the sample. Here you see a nanoantenna made by 3 gold discs. And this is an experiment which is quite interesting and very versatile. Point by point, by moving the emitter with respect to the sample, you get the topography of the sample. And then by coupling it with a microscope, you can excite the emitter and detect its fluorescent emission, and then measure point by point the intensity and the decay rate. So this is a very powerful system because it allows the direct characterization of the electromagnetic field in the near field of the sample. It's a versatile system because with that you can study dielectric and plasmonic samples. You can use different emitters. You can go down to a resolution of a few tens of nanometers, which is good. And you can get a nanometric control of the emitter position, which was let's say, the ingredient that was still missing. So, I just stopped the movie. So here I will show you how we were managing to have an emitter graphed to the tip. Because if you look at the numbers, okay, numbers are very small in this case, okay? So here you have, this is an optical image of a sample which is just a cover slip on which we spread a lot of polystyrene beads, that, fluorescent, that are 100 nanometers large, so they are sub-diffraction limit. So this image is diffraction limited. Here you see a shadow which is the tip, but we don't really see the tip. We don't know where is the apex. And the difficulty is to pick only one emitter with a tip. And just for the small story, okay, with the PhD student who was working with me at that time, we tried a lot of things. We tried very difficult protocol, and nothing was working. And this video was acquired on a Friday late afternoon. We were just, we didn't know what to do, and we just said, well, let's try to play soccer with the beads. It's Friday afternoon, and then we go home for the weekend. And this is what happened. Okay, so the extremity of the tip is somewhere here. So we just move the sample underneath the tip, try to push, but we don't know where is the apex of the tip. So we move and we try again, and the emitter will stick on the tip. We were very, very happy. Also because all the very difficult things that we were trying up to that moment were not working. And, well, this simple thing just worked. So, of course, now I'm saying that it's easy. It's not that easy. You want the emitter to be photostable over several days because once it is on the tip, you want to keep it and to measure with it. You don't want it to blink. You want it to have a very small size. You want it to be bright. So it's quite a hard experiment. But thanks to this experiment, we could do quite a lot of things. I'm not going to enter into the details of all this. So we could study plasmonic antennas, dielectric antennas, but also other kind of environments like tapered nanofibers. So here you have to imagine a very thin nanofiber, which is a tapered one. In the very thin region, the diameter is like 100 nanometers. So you have evanescent fields leaking out from this part of the fiber. And with our fluorescent SNOM tip, we were able to fly on the top of the fiber. We were like tightrope walkers on the skyscrapers of New York, okay? And we were able to map the intensity of the field on the top of the fiber. We were also able to study hybrid planar waveguides, which are interesting because these are high dielectric index waveguides which are dressed with plasmonic nanoantennas in order to increase the coupling efficiency of the fluorescence from the outside to the waveguide. And we were able also to develop a method to determine, to disentangle the radiative and non-radiative contribution of the local density of states. Okay, so we said that from the very beginning, the easiest experiments, which are based on statistical measurements, one can go to more difficult experiment, but much better controlled in the terms of the positioning of the emitter, which are these near-field scanning probe microscopy setups. But I have to say that even if it's possible to study a lot of different environments with this kind of setups, we were a little bit sad because there is a major drawback here in this kind of setup, that is the presence of the tip. Because the tip is a part of the environment. And even if you choose, like we did, a tip which is a silica tip, very thin, in order to reduce the perturbation that it induces in the environment, but it is a part of the environment, okay? So we said, what can we do to remove the tip? And we started to look in a different field, which is biophysics. In biophysics, when you look at, what people do in order to image processes in a cell, for example, what they need to have is super resolution. So they put fluorescent emitters and they get very, very nice images with resolution of a few nanometers. And I'm going to explain you how they do that. But looking at biophysics, and this is a point which is very important to me. I mean, when you are in a domain, you don't have to be afraid to go and look to what other people do in other domains. Because when you look at nanophotonics and biophysics, I mean, we have quite similar challenges to solve. One of those is to measure, I mean, to image our samples with nanometric resolution When you want to measure the decay rate, they also do it in biophysics in order to measure, for example, the interaction between proteins or to measure the distance, very small distances between two different fluorophores. So you want to have a very large time dynamics. You want to do, for example, multicolor image to measure the local density of states in the case of the nanophotonics at different wavelengths. You want to do correlative microscopy. Well, the example that I was giving just a few minutes ago of measuring TEM, I mean, image the sample with TEM and comparing it with optical measurements. This is also something that can be that is interesting for biophysics. And therefore, we said, okay, maybe biophysics has something to teach to nanophotonics. Okay, so a small parenthesis in this field. Okay, so in biophysics, there are a lot of techniques that are used for super resolution. Of course, today I'm not going to talk about everything, but I'm going to focus on only one technique, which is single molecule localization microscopy. So what happens? Imagine that here you have a fluorescent emitter and you want to image it through an imaging system. I'm not saying something very new if I say that the image that you are going to find on a CCD camera is not a point-like image, but it's the point spread function, which has a size which is of the order of the wavelength divided by the numerical aperture of the imaging system. So, and of course, this is something that is not new for you, I think. There is the resolution, so all the images that we do in optics are diffraction limited because there is a resolution limit, which is the Rayleigh limit, that tells you that if you have two objects that are emitting at the same time, then if their distance is smaller than the radius of the Airy disk, so the distance between the maximum and the first zero, then you cannot resolve them. And this is true, of course. But if I don't have two emitters, but I only have one emitter on the sample, then I measure its PSF, I can make a Gaussian fit of it, and I can point the center of the PSF with a precision which is much better than the size of the PSF itself. And by using this method, I can actually show you that I can go down to a resolution which is, or a localization precision which is of the order of the nanometer. So just put some very easy, some numbers on a very easy calculation. So the diffraction limit, as I said, if you take a wavelength of 500 nanometers and a numerical aperture of 1, it's 250 nanometers. When you make a fit, a Gaussian fit to the PSF, and you try to point the center of the PSF, the localization error is the diffraction limit. I mean, with a very simple statistical approach, is the diffraction limit divided by the signal-to-noise ratio. So n is the number of photons. If you take a Poissonian distribution, the signal-to-noise ratio is n divided by square root of n, which gives you square root of n. And so if you detect 10 to the 4 photons, then the localization precision that you have on a single molecule that is detected go down to a few nanometers, to 2 nanometers. And this is important because then if you label all the sample with molecules, and you are in a regime in which the molecules are not switching on, emitting all at the same time, but they are stochastically blinking, okay, then you can reconstruct a super resolved image, how it works. So here, I have molecules everywhere, So if I make just an integrated image, I have a diffraction limited image. But now if I have molecules that are blinking, frame by frame, there is only one molecule that emits. So for this frame of the camera, I point the center of the point spread function. The subsequent frame will show two other different molecules, these 2 points. And if I wait for a sufficient long time, I can reconstruct all the image in a super resolved way. So this is how the experiment looks. So you have molecules blinking everywhere, and I don't know if you can see it clearly. You can reconstruct in a super resolved way the sample. So each point is something like a few nanometers large. Okay, so this kind of technique has been applied to the study of nanophotonic samples and to look at different things. So you can measure the fluorescence intensity. Here you have a few examples, 3 nanodiscs, silicon nanowire. Here it was a DNA origami. Here you have 3 different molecules and a gold sphere here. But the thing is that when you measure the local density of states by measuring the fluorescence intensity, this is a measurement that is much less robust than what you get with the decay rate. The very first simple reason is that when you measure the fluorescence intensity, you have to measure in a very accurate way the number of photons, and this depends on the efficiency of the detector, on the collection angle, it depends on so it depends strongly on the angular emission of the emitter. But when you measure the lifetime, you don't have all these dependencies. And so people also looked at the lifetime, but in this case, the work that you find in literature are either constrained to the study of specific samples, here periodic samples, or they were constrained. I mean, they were quite heavy to develop. Here, for example, you have a quantum dot. This is a very hard experiment, a quantum dot that was just flowing on the top of a silver nanowire, and it was flowing thanks to a very precisely controlled flux inside a microfluidic channel. Or here, in this other example, you have a quantum dot that is running on the top of a microtubule, and this is the nanostructure, but of course, it is very hard to know. I mean, the microtubules were just randomly spread on the sample, and the quantum dot goes on a very precise trajectory, so you cannot map the density of states everywhere on the sample. And so what we decided to do at Institut Langevin was to develop a new technique, a very general one, in order to be able to study any kind of sample based on these techniques, single molecule localization techniques. So the experimental setup is very simple. You have a pulsed laser that goes on the sample. Here you have fluorescent molecules everywhere. You excite the sample in wide field, and then you detect the fluorescent photons through the same microscope objective, and you split the fluorescent photons in 2 parts. The first part is detected on an EMCCD camera, and what we do is exactly what I just said. So the sample is made of stochastically photoactivatable molecules that blink here, and for each PSF, you point the center of it, and you localize the molecules. And at the same time, the second half of the photon is detected by a sputtle ray, which is able to reconstruct thanks to which we are able to measure the lifetime of each single emitter that is emitting here with a time resolution which is very, very good. We can go down to lifetimes of 10 picoseconds. And so by putting together the information about the position of the emitter on the sample and the lifetime of the emitter, we can reconstruct an image, a super resolved image of the lifetime. Here what you see is that the color codes the decay rate, or the decay rate of the emitter, and therefore the local density of states. On a real sample, this is what we get. So this sample is just a simple silver nanowire, on the top of which we have a lot of fluorescent molecules. We measured the intensity and the lifetime of each one of those. And here is the experimental data. So each tiny single point here is a single molecule that has been detected. The size of the point is about 10 to 15 nanometers, which is our localization precision, and the color codes the decay rate. So here you see, in a very simple way, something that is that the decay rate goes up when the molecules are close to the nanowire. And this is due to the presence of the nanowire, because it introduces absorption and it has some plasmonic modes that can propagate on the wire. Yep.
How do you put the information together from the 2D imaging and
We make a correlation. We correlate the temporal signals of the camera and of the SPAD.
Yeah, but on what time scale? Because this is milliseconds.
Yeah,
this is nanosecond.
it's a very good question. Sorry. Okay, so yeah, you're right. Lifetimes are the order of nanoseconds or picoseconds, but here we have milliseconds. Okay, so you have to keep in mind that the molecules that we use blink. I mean, they are on and they bleach, okay? And here we play with our excitation power, etc., in order to have like a bleaching time of the molecule, which is about 30 milliseconds, which is one frame of the camera. In these 30 milliseconds, what we do with the SPAD is that we measure continuously the intensity, and therefore we see a burst, which is of course not resolved at the nanoseconds level, okay? We just measure continuously the fluorescence intensity, and we see a burst. So we correlate this burst, the appearance of this burst, with the appearance of this burst on the camera, and this gives us the knowledge of which molecule we have detected here, and which one what is the associated time signal.
So it's one molecule per frame, right?
Yeah, well, this is the easy way to explain it. Okay. It's not one molecule per frame. We have more molecules per frame, but the very important constraint is that you don't have to have two overlapping PSFs. And here we have one more constraint, which is quite hard and slows down quite a lot our experiments, which is that we have to be sure that this molecule here has been detected by one SPAD, and there was no two molecules detected at the same time by the same SPAD, okay? Because in this, otherwise we cannot distinguish between two different lifetimes. And since, in order to have field of view of the order of 10 micron, like here, what we do is that we conjugate the region seen by the SPAD with something that is more or less 1 micron, okay? 1 micron on the sample. So this is the size of the region seen by the SPAD. And that means that we cannot have more than one molecule emitting at the same time in a region that is 1 micron large, okay? And this is quite a big constraint because, well, the rate at which you switch on your molecules is lower than on normal, let's say, biophysic super resolved experiments in which the blinking of the molecule, yeah, it's much faster.
Do you know why there's this periodicity along the wire?
Yeah, this is another, this is just, depends on how we measure it. So I didn't mention, but we use a 8x1 spad array, okay? So each spad sees 1 micron on the sample, and this is the region seen by, by each one of the spads. Of course, by changing the optical system that you use to detect the light on the spad, we can change the overlap between these regions, but it's a choice that we made here. Okay, so to finish, I would like to show 2 recent results that we obtained with thanks to this system. Also, to show you that, well, maybe you have the feeling that we have everything because we have single molecules on the sample. We know where they are. We know how they emit. We can measure the intensity, the lifetime. But I forgot to tell you something that is important that I will tell you in the next slide. So, why I choose these 2 examples? Because these 2 examples are very interesting because in this first one, the nanostructure is a dielectric nanoantenna is made by gallium phosphide. And in this other example, we look at a plasmonic nanostructure. These are called hollow nanocones, which are arranged on a periodic array. So first of all, I'm going to talk about dielectric nanoantennas. I still have some time, no? Because okay. Huh? A few minutes. Okay. My chronometer doesn't tell that. Okay. So why dielectric antennas are interesting? Because the total, when we measure the lifetime of the emitter, we measure, the decay rate of the emitter, we measure the total decay rate. But if you want to have a source that emits a lot of photons in the far field, you want to have a large contribution of the radiative decay rate and a small contribution of the non-radiative decay rate, a small contribution of the absorption. So dielectric nanoantennas are interesting because since they are made by dielectric, in this case gallium phosphide, so gallium phosphide has a very high, quite high refractive index, 3.3. So you increase, you have a very low absorption, and so when you, the gamma is dominated by the radiative part. And for this specific nanoantenna, one can show that if you do numerical simulation, with a plane wave that arrives on the nanoantenna, you have a very nice and bright hotspot here. Which tells you that you will probably have a very nice enhancement of the local density of states here. And indeed, if you do the experiment that I've shown you, so here you have 3 different gallium phosphide dimers. Here you see each point is a single molecule that is detected. The size of the point is 15 nanometers. And what you see, and the color, of course, is gamma over gamma 0. What you see is that for the 3 dimers that you have here, in the middle of the gap, we have a very high per cell enhancement of a factor of 30. This is relatively high for a dielectric structure. And then almost, a very low per cell enhancement on the rest of the structure. So this just to show you on a single molecule, what are the decay histograms that we are able to measure for 3 different positions in the gap, the yellow one, 9 nanoseconds to the -1, on the top of the cylinder, the blue one, and on glass, on the substrate, 0.3 nanoseconds to the -1, with a very nice signal-to-noise ratio. Okay, why I was saying that I was hiding a very important point. It is because up to now I told you that everything is beautiful, and then when I have a dipole that emits and I make an image of it, I measure its point spread function, its naive function, and everything. I make a Gaussian fit, it is symmetric, and I measure the position of the dipole with a very large precision. This is true. But the problem is that here we are in the realm of nanophotonics, so we deal with resonance structures. And when the dipole is coupled to a resonance structure, depending on the orientation of the dipole, depending on the coupling, but the PSF is not anymore as nice as this one. It is modified by the presence of the nanostructure, and if I make a Gaussian fit on that, but I will localize the emitter here while its real position was there. And actually, this distance can be as large as 200 nanometers. And this is a problem, okay? So we measure the apparent position and not the real position. And this depends on the structure, on the dipole orientation, on the distance, on the coupling to the structure, on the wavelength. It depends on quite a lot of things. So I don't have, we are working to the solution of that. We already published a paper with a method to solve this problem, but I would like to have better results. We are working on it. For the moment, what I can show you is this. So this is just, so I'm going back to the previous sample that I was showing you, this dimer made of gallium phosphide. Here you have FDTD simulation of the radiative part of the local density of states on the dimer. You see that in the middle of the gap, you have a quite high per cell enhancement, as in the experiment. But then if you look closely to the shape of the local density of states here, you see that in principle, we should be able to see an enhancement also on the outside of the dimer. And this is something that we don't see at all on our data. But now, if instead of simulating the LDOS map with the real position, we simulate it exactly as we do in the experiment, so we measure the apparent position, then you see that on the gap, okay, we have a gamma enhancement, which is the good one, but all the other points are bunched on the top of the cylinders with an enhancement which is small. And this is really close to what we observe experimentally. And actually, by looking at the PSF that we measured, this is the simulated ones and these are the experimental ones, this is proved. I mean, here you have a molecule which is in the gap. The PSF is gently symmetric. We don't make mislocalization error. But now, if the molecule is displaced with respect to the gap, then the PSF is distorted, and then we make an error in the position. Okay, so I'm going to conclude. I just want to show you a last image because I find it beautiful. So, and it shows the potential of this setup. So what you see here, again, it's super resolved single molecule images of gamma over gamma 0 and the intensity on a structure, so I go back, which is like this one, is a periodic array of gold nanochimneys that you can see here. And here you see that we were able to reconstruct the periodic array and that we are able to see modification of gamma over gamma 0 inside the pillars. So I'm not going to give the details about that, but oops, no. We were able to understand the variation of gamma on these very small structures. Okay, so to conclude, the general summary. So what we have shown to you is that the study of the local density of states is very interesting and very powerful to study the interaction between molecules and the environment. The local density of states is a quantity that counts the number of modes of the field available for the decay of an emitter. Remi showed you that the enhancement of the local density of states with respect to an homogeneous medium is equal to the Purcell factor and to the emitter power, the modification of the emitter power, and is related to the green function of the environment at the position where the emitter is and its emission frequency. Then we showed you that it is possible to map the local density of states by measuring the decay probability of an emitter, by measuring gamma, and therefore if I measure a large gamma, it means a large local density of states, and if I measure a small gamma, it means a small local density of states. And to conclude, I've shown you that it is possible to position single emitters with nanometric precision in the environment to excite and detect their fluorescence intensity and lifetime. And I've shown you the experimental developments of these last years. And I want to finish by thank all the people who worked with me, Romain, Remi, also Ignacio Zedin and Clément Cabriel, who helped me quite a lot for all the topic of single molecule localization measurements, Yannick de Wilde, and all the PhD students and postdoc who worked on all the data that I've shown you today. And this is, well, the group as it looks like now. Thank you.